Okay, 9.3 is electric field potential and energy. This portion is very similar to 9.2, so it draws an absolute parallel with gravitational field and potential energy. So just like in gravitational fields, the potential energy in electric fields is given by Q over 4 pi epsilon naught r. So in gravitational potential energy, we had derived that the potential energy was Gmm over r, and there was a negative sign. Now the negative sign indicated an attractive force. Okay, so when the force is attractive in nature, like we had described, in bringing a mass m from infinity to a point in the field, there is negative work done by the external force. Okay, and therefore the potential energy is negative. In electric potential energy, we do not need to include the negative sign because the signs of the charges will take care of that automatically. If the charges are unlike charges, the force would be attractive and we would have a negative potential energy. However, if both the charges are like charges, then the force would be repulsive, and therefore the potential energy would be positive. Why? Because in bringing a charge against a repulsive force from infinity to a point in the field, the external force must do work in the direction of the displacement, and therefore the potential energy would be positive. So that's how electric potential energy is defined. Electric potential again is defined as the work done per unit charge in bringing a small positive test charge from infinity to a point in the field. So it would simply be EP divided by Q. Okay, so that would be Q over 4 pi epsilon naught r. Again, very similar to the gravitational potential. Now the units you should take note over here. This is joules. The gravitational potential, okay, this was also in joules, but this was in joules per kilogram. Okay, the potential in electric fields, the electric potential is measured in joules per coulomb. Okay. Now joules per coulomb, by the way, is also volts. Now state and apply a formula relating electric field strength to electric potential gradient. So let's say there are electric field lines in this direction, okay, and from point A there is a charge which needs to be moved from point A to point B, and this distance is delta x. Okay. Now the work done, let's say a force F does work delta W in moving the charge Q, okay, from A to B. So the work done would be F times delta x, right? And now, since this force is in the opposite direction to the direction of the field, the magnitude or the value of this force would be negative Q times E. Why negative? Because the E field is in this direction and the force applied is in the opposite direction. Okay, and by definition, so therefore this will be, yeah, and by definition the work done is defined as the charge multiplied by the potential difference between A and B. Okay, so from here we have the E field is the negative of the gradient of the potential versus displacement graph. So similar to how we got the gravitational field strength as the negative of the gravitational potential versus displacement graph. Okay, so whenever you have the electric potential graph, you can simply take the gradient and the negative of the gradient to find the electric field strength at that point in the field. So page 16 has a few examples of this which makes it clearer. Okay, 9.3.4 determines the potential due to one or more point charges. Again, just like gravitational potential, we will do an arithmetic addition of the potential. Why? Because electric potential is a scalar quantity, whereas the E field is a vector quantity. Okay, so if you have to add up the potentials due to multiple charges, you would simply do a arithmetic addition. Okay, 9.3.5 and 9.3.6 basically describes the pattern of equipotential surfaces. Again, just like we had in gravitational fields, we have electric field lines, okay, and the equipotential surfaces would be at 90 degrees to the electric field lines. Okay, so similarly you can see some patterns. Again, these electric field lines would be either radially outwards or inwards depending on whether this is a positive charge or a negative charge. So the end result should always be that the equipotential surfaces are at 90 degrees to the field lines. So some of the examples are given here at the bottom of page 17. And remember that in moving a charge from one point to another point on an equipotential surface, the amount of work done is 0. And again, equipotential surfaces are always perpendicular to the lines of force. Now, finally, just like we have near the surface of the earth, we have the assumption of a parallel field, right? We have the assumption of a parallel gravitational field. In a similar fashion, we have parallel plates, parallel electric plates. Let's say this is a positively charged plate and this is a negatively charged plate. So we have electric field lines moving from positive to negative. Okay? Notice that we had talked about this in chapter 6. The electric field lines must have uniform spacing, and at the ends we must draw fringe lines to show that the electric field is not constant anymore, is not uniform anymore. Anyway, over here we have equipotential surfaces again, which should be perpendicular to the electric field lines. Okay, so each of these lines has a certain potential. So for example, if you have 0 volts here, 50 volts here, or rather 40 volts here, these will be equally spaced equipotential surfaces. We have 10 volts here, 20 volts here, and 30 volts here. Okay, so those are equipotential surfaces between parallel plates. Now, page 18 has a good summary of the distinction between gravitational quantities and electrical quantities and their corresponding electrical quantities. So that's a good summary of the table. 9.3.7 is simply using these concepts in examples. So going through these examples should help strengthen the concepts better. Yeah, so that's the end of 9.3, and now we move on to 9.4. Okay, section 9.4 is orbital motion. So let's get started with that. Let's say on the planet Earth here, okay, we have a man standing here who is holding an object of mass m. Okay, so this mass m is being attracted to the planet here by a force gmm over re square. Gmem. Let me write that a little bigger. Gmem over re square. Okay, me is the mass of the earth, re is the radius of the earth. Now let's say this object is thrown in this direction, is going to fall towards the earth. Okay, if it's thrown with a greater velocity, it's going to fall a little further. But let's say it's thrown at such a high velocity that as it is falling, the Earth's curvature is making the Earth slip away from under it. So it's falling towards the Earth, but because of the Earth's curvature, it never hits the Earth's surface. So it continues on in this circular motion. Okay? So at this state, the object is said to be in an orbit around the Earth. Okay? So let's say, so when it's moving in a circular motion, we can say that the gravitational pull, which is the only force acting on this object, is equal to the centripetal force on this object. Okay? So if you resolve this, you will get your velocity equals under root of gme over re. You can see this being done on page 20. Okay? And we also know that gme over re squared equals g naught. Right? So therefore, this velocity is under root of g naught re. Okay? So this is approximately 8 times 10 to the power 3 meters per second, which is saying that in an ideal scenario where you can ignore the effects of air resistance, if you throw an object horizontally at 8,000 meters per second, then it should continue on in an orbit around the Earth. Okay? Now we can see that this velocity is well inversely related to the the radius of the Earth. But in this case, the radius of, or rather the distance between the center of the planet and the object itself. So which means if the object was further away, the velocity required would be lesser. Okay? And also, so that this is how we can send satellites and keep it in an orbit around the Earth. Firstly, when satellites are higher above, they need a lesser tangential velocity. Secondly, there are lesser resistive forces up above the atmosphere, and therefore they can continue on in an orbit or an orbit around the Earth without the need for an external source of energy, a constant external source of energy. Okay, so so from here we go on to Kepler's law.